Hello everyone, and welcome to our video on 9.1, starting chapter 9, which is over review of radicals and quadratic equations. So mainly we're going to be talking about simplifying radicals in this video, which is going to be a stepping stone for the rest of really the year, especially chapter 9, because we're going to be spending so much time on right triangle trig. So as soon as we have right triangles, radicals do come into play quite a bit. So before we get started with number 1, I want to remind you that when we are splitting radicals to simplify them, we want to split square root of 98 into two square roots in what multiplication fact ends up multiplying to be 98. So before we do this, we want the first one to be a perfect square and the second one not to be. So if you'd like to, feel free to write down the perfect square list if you need it. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, and 144, and so on. I would say that these are the most popular ones. And so when we look at 98, I would only divide by these perfect squares, because you know you need a perfect square in one of the radicals. So does 4 go into 98? It does not. Does 9? No. 16? No. 25? 36? Now 49 though, I would say if you're ever not sure what goes into a radical, usually 49 comes to help, and it does in this case. 49 times 2 is 98, so we could split this into root 49 times root 2. Which one of these simplifies? Well, only the perfect square, so the answer would be 7 root 2. Number 2 is a little different because we have variables involved, but I'd like to remind you that anything with an even exponent is a perfect square. And the reason for that is because you might recall from AAA or AATH that anything to the 1/2 power, like 9 to the 1/2, is the same as the square root of 9, because you assume that there's little 2 there for square root, and this is really 9 to the 1st. So these two things are equivalent. So even powers are perfect squares because they're divisible by 2. So what we're going to do here is make two radicals, and we're going to put all of our perfect square roots over here and all of our non-perfect ones, or whatever's left over, in the second one. So because 9 is a perfect square, we would put that in the first pile. X to the 4th is also perfect because there's an even exponent. However, y to the 5th is not perfect, but what we could do is think about what is the closest perfect square to 5. Well, if we put 4 of the y's over here and 1 of them remaining, we could say that this splits up. And this works up with exponent rules too, because y to the 4th times y is y to the 5th. So if I continue to simplify this, the square root of 9 is 3. The square root of x to the 4th is x squared. The square root of y to the 4th is y squared. And then we would just leave square root of y alone. Number 3, you might remember something called rationalizing, which means that we cannot have a radical in the denominator. And this is going to come up quite a bit this semester. So if you want to get rid of the radical in the denominator, we would multiply top and bottom by root 2 over root 2. The reason this works is because root 2 over root 2 is really 1. So you're not changing what the final answer is, you're just changing how it looks. So if I multiply straight across, we would get 7 times root 2 is just 7 root 2. Root 2 times root 2 is really root 4, which really ends up just being 2. So my answer rationalized would be 7 root 2 over 2. And we would leave our answer like that because we can't take anything out of 7 and 2. Number 4 is a similar idea. We cannot have a square root in the denominator. So we could do this problem two ways. One way we could do it is just like the previous one. We could multiply top and bottom by root 3, and if we did so and multiplied across, these are like terms because they both have square roots. So this would be the square root of 45 over the square root of 9, which would really be the square root of 45 over 3. However, like the first example, number 1, we could split 45 into perfect square and not. And so if I think about my perfect square list, 1, 4, 9, 16, 25, I know that 9 goes into 45 evenly. So we could split the top to be root 9 times root 5 over 3, which is really 3 root 5 over 3. The 3's cross out, so my answer is just the square root of 5. Now, if you're interested, you could have done this problem a lot more quickly. If you notice that there's a square root on top and bottom, this is the same thing as saying this is the square root of a big 15 divided by 3, which then equals the square root of 5. The reason we couldn't do that here is because this does not have a square root on it. So you could either do the way in blue or the way over here in purple. Number 5 really means if you have 5 root 3 squared, that is really 5 root 3 times itself, 5 root 3. And no, this is not FOIL because we don't have any plus signs here, so we're only multiplying the, quote, I call them like terms. We're going to multiply the regular numbers together, and then we're going to multiply the root 3's together. So if I multiply the 5's, I would get 25. If I multiply the root 3's, I would get root 9. So this is really 25 times 3, so my answer is actually nice of just 75. If I look at number 6, what we want to do is we have a radical times a radical, and so when we have that situation, this is the same as the square root of 6 times 18, which would be the square root of 108. And if I think about my perfect squares, 1, 4, 9, 16, 25, 36, and so on, when I first take a glance at these particular ones, I notice that both 4 and 36 go into 108. So what if I had tried to split this into 4 times 27, because 4 times 27 is 108. If I did that, what I want you to notice is that yes, this does reduce to 2 root 27, but you wouldn't leave your answer like this. You would have to keep splitting root 27. And you could do that, leave the 2 in front, and split this into root 9 times root 3. Root 9 is really just 3, because you're taking the square root of 9, times 2 root 3. There is no number times itself that equals 3, so that's why we leave it in the square root. So your answer this long way is 6 root 3, which is correct. But if you notice that 108 does end up being the multiplication fact of 36 times 3, we could split this into root 36 times root 3, and my answer more quickly is 6 root 3. So the reason I wanted to do this once was to show you that on a test, if you do split it like this first and you do notice you need to keep going, you will get to the right answer eventually. But it is good to try to find the biggest perfect square possible. Number 7. So now we're leaning away from multiplication and dealing with combining, because notice that now we're trying to add square roots. And what you need to notice or remember from your past is that in order to add radicals, the radicand needs to be the same. So this is called the radicand, and the number under the square root has to be the same as a quote like term. So if I have 2 root 5's plus 4 root 5's, my answer would be just 6 root 5. Just like if this was a 2x plus 4x problem, the answer would be 6x because you're combining like terms. It's the same idea here. Number 8. Now, as is, I cannot do anything with this answer because root 75 and root 12 are not like terms. And yes, if I go back to the previous slide, yes, I can multiply any radicals that I want, but I cannot add or subtract any radicals that I want. So what I can do is see if this radical can be split into 2 radicals, one perfect square, one not, and split root 12. If I think about my perfect squares, 1, 4, 9, 16, 25, 25 times 3 is 75. And if I think about my multiples of 12, 4 times 3 is 12. So if I reduce this, this is a perfect square. So we get 5 root 3 minus 2 root 3. And now that my radicands are the same, I have 5 root 3's minus 2 of them. So I have 3 root 3's in the end. Number 9 is similar, that right now we cannot add these radicals because the radicands are different. But what I could always do is think about splitting the radicals that I currently have. So if I think about 125, I think about money. So 25 goes in. There are 5 quarters in $1.25, so 25 times 5. And if I think about 20, the perfect square of 4 goes in, 4 times 5. So this reduces to 5 root 5 plus, the 3 is multiplying, so it's 3 times 2 root 5. So we have 5 root 5 plus 6 root 5. So my answer is 11 root 5s. Number 10. If you would like to stop and pause and try this one on your own first, that would be a great idea. My suggestion is if any radicands, the numbers underneath don't match, see if you can split it and go from there. So if you'd like to try this one, please pause your video now. Alright guys, so my final answer for number 10 was 7 root 6. Please note that there's really a 1 in front of that root 6. I split root 24 into 4 times 6, and 6 does not split anymore because there is no number times itself that is 6. And even if I split 6 into 3 times 2, neither are perfect squares. That doesn't help me, so I just left it. So I ended up with 4 root 6 plus 2 times 2 root 6, which was also 4 root 6. So 4 root 6s plus another 4 is 8, minus 1 got me 7 root 6. Number 11 and 12 are using the distributive property, and sometimes you do end up doing FOIL, but this is more for just looking at the rules. So if I would like to distribute in the 3 root 2, we just need to think about what we can multiply and what we can't. So multiplication, we have more freedom. So we can multiply all radicals. So this would be 3 root 4 plus, if I do 3 root 2 times root 6, that would be 3 root 12. So my goal is to simplify the radicals as much as possible. Now, lucky for us, this first one is really 3 times 2, because root 4 is a perfect square, plus 3, not a perfect square, but I could split root 12 into 4 times 3. So I have 6 plus 3 times square root of 4 is 2 root 3. So I have 6 plus 6 root 3. Now, this is the final answer, because in order for radicals to be like terms, they need the same radicand. So because this 6 does not have a root 3, they are unlike terms, so I leave my answer like this. Number 12. What I want to do is distribute the 2 root 5 into both terms. So if I multiply the 2 root 5 times the 2 root 10, we multiply the integer numbers, the 2 times 2. So I'd get 4. Root 5 times root 10 is root 50. And then I want to multiply the 2 root 5 times the 3 root 3. So I multiply this times this. So 2 times 3 gives me 6. Root 5 times root 3 is root 15. So if I keep simplifying both, 4 stays. Root 50 can split into 25 times 2 plus 6. Now here, as I mentioned earlier, 15 could be split into 5 times 3, but 5 and 3 are both not perfect squares. So this step does not help me at all. So I'm going to keep this as just 6 root 15. This side is really 4 times 5 root 2, which would be 20 root 2 plus 6 root 15. Now because these radicands are not the same, I cannot add or subtract anything that's not a like term. So this would be my final answer for number 12. Now the last examples here are all using or solving quadratic equations. I'm going to go to a second video for these, so feel free to stop this video and go to the second one. Thanks guys.